Okay, so we've wrapped up the mechanism design segment of the course. You might recall from the first lecture that that was part 1 of 3. So we're going to start part 2 of the course today. And part 2 is about understanding the inefficiency of equilibria in games. So this area is motivated by the actually fairly common scenario where you don't have the luxury of designing a game, of designing the rules from scratch. Okay, so far we've assumed that you knew some information about the environment and you got to pick the rules of the game so that the outcome of strategic behavior was what you wanted, or as close to what you wanted as possible. So now we're going to look at games, in the most basic form, games that just occur in the wild, okay, which already exist, where strategic behavior is already there. We want to know, which ones function well and which ones don't. So when the games in the wild, if you will, nevertheless have near optimal equilibria. So sometimes they do, sometimes they don't. Our goal is to have a delineation between the two, to really understand which are the good cases and which are the bad cases. Now let me open with just some comments about the difference between this part of the course and the previous one. So on a technical level, our analyses of the inefficiency of equilibria, or the so-called price of anarchy, they'll have a different flavor on a couple of levels. So first of all, the games will generally not have dominant strategies. Again, we didn't have the luxury of defining them. In fact, dominant strategies are pretty rare. So we're actually going to have to analyze non-trivial equilibria. We'll start with Nash equilibria, but look at a couple of other equilibrium concepts as well. As you might expect, if we don't have the luxury of designing the game, we're typically not going to get full optimality. So there's certainly going to be no analogous result as like the VCG mechanism, which says in principle you can get full surplus if you can design the rules of the game. In fact, forget about full optimality, even approximate optimality. In some sense, the game has to have fairly special structure. Okay? So the hope is that there are application domains of interest, assumptions which on the one hand are strong but are also met in interesting scenarios where we can prove that equilibria are near optimal. And I'm happy to say we now have about 15 years of experience of different domains where you can actually prove that equilibria are guaranteed to be close to optimal. One thing that'll be simpler in this part of the course is there won't be private information. Okay, so for example, in a traffic network, all players are going to be fully aware that all of the players just want a shortest path. They just want to get to their destination as quickly as possible. By contrast, in the auction setting, I didn't even know what other people wanted. So if you asked me, would this other bidder prefer to win the item at a price of 10 or lose? I don't know. Depends if the valuation is at least 10 or not, and I couldn't answer that question. Right? In rock, paper, scissors, if you ask me, given that I'm playing rock, would they prefer to play scissors or paper? I know the answer. I know they prefer to play paper. Okay, so it's going to be mostly full information games. For those of you who take the sequel course in the winter, there'll be a nice dovetailing of these two areas, and we'll look at things like the inefficiency of Bayes-Nash equilibria, which is a way of modeling private valuations in this kind of setup. But for this course, we'll just stick with the full information case. I guess one final historical comment. So in mechanism design, I taught you a mixture of classical economic theory. So Meyerson's theory of optimal auctions being a good example. And the novel contributions coming from computer science have been novel questions or novel extensions on top of this classical economic framework. One thing that's cool about this part of the course is really these questions essentially were never asked, certainly never asked systematically until about 15 years ago when that came out of the computer science community. So this idea really has its genesis in a paper of Koutsoupias and Papadimitriou, two computer scientists, back in 1999. The following year, I started working on it myself with my PhD advisor, Eva Tardos. Okay, so any questions before we get started? Let me quickly remind you of what I mean by a game in the wild. Okay, this is going to be Brace's paradox. We talked about this in lecture 1. Let me jog your memory. So what you want to think about is you want to think about traffic. Okay, and computer scientists who have studied this were motivated more by data networks, communication networks, but the model goes back, as you might expect, to transportation scientists. And you may as well think about morning commuters leaving at 8 a.m. from a common origin, S, to a common destination, T. And of course, drivers take whichever route they want. Okay, there's no central authority dictating which route you take from point A to point B. And we're going to assume always that they want to minimize their travel time. And what makes it interesting, the reason you as a driver care about what other drivers do is the congestion on roads goes up. And as it goes up, your travel time increases. So in the basic brace paradox network, we have two kinds of roads. We have very simple ones, labeled by the cost function c of x equal 1. That's a constant cost function. So that says driving on this road takes an hour no matter what. Okay, so think of it as a long road with an infinite number of lanes. But then we have these other roads, c of x equal x. So these are roads that get congested as more and more people use it. Okay, so there's 1 unit of traffic overall. If x units, or an x fraction of the traffic, takes one of these links, we assume it costs x hours. Okay, so if half the traffic's on one of those links, it takes 30 minutes to cross that particular link. Okay? So what we did on lecture 1 is we first asked, what kind of equilibrium would they settle into in this basic network? Okay, so this already is a game without any dominant strategies. If more people, for whatever reason, are using the top path, you'd prefer the bottom one. If more people are using the bottom one, you'd prefer to use the top. So your quote-unquote best response, your best action, depends on what others are doing. Okay, so there's no dominant strategies. But by symmetry, we argued that we expect traffic, if these are the same people listening to the traffic report day after day, there's really no reason to prefer one of the paths over the other. So we'd expect a 50-50 split. Okay? For an average commute time of 90 minutes. The reason it's called Brace's paradox is when you augment the network by a teleportation device. So 0 cost to teleport from the midpoint of the top path to the midpoint of the bottom path and no congestion. Now all of a sudden I've introduced a dominant strategy. So it turns out no matter what the other drivers do, you always want to use this teleporter. It's always in your best interest. The problem is that when everybody rushes to follow their dominant strategy, and 100% of the traffic is on the zigzag path, the congestion on the upper left and the lower right links have gone up to 1, and the commute time has gone up to 2 hours. Okay? And because this is the dominant strategy of all of the drivers, there's no other equilibria. This really is what happens. And people have run lab experiments. If you introduce the teleporter, this is really what happens. Okay? People wind up in this, this equilibrium with a higher commute time than before the introduction of the teleportation device. So the paradox was, unlike an optimization where adding more feasible solutions can only make you better off, here you add extra options and the equilibrium gets worse. So the commute time goes from 3/2 to 2. Okay? And so in particular, in this new network, we're asking when are equilibria optimal or near optimal. Well, the equilibrium in this new network is certainly not optimal. Okay, so it turns out the optimal thing, even after the teleporter, the best thing to do is just ignore it and stick with the 50-50 split. Okay? So in the new network, the equilibrium has commute time 2, but the optimal commute time, if you in principle had dictatorial control everybody, you could achieve a commute time of 90 minutes. So the price of anarchy is just defined as the ratio between these two quantities. You look at the performance achieved under strategic behavior, the performance you could hypothetically attain if you could dictate actions to everybody. That's going to be a ratio at least 1. In this case, it's 4/3. Okay, so POA in the new network after the teleporter equals 2 divided by 3/2 or 4/3. Okay? And so the price of anarchy in these kinds of networks is just defined as the equilibrium commute time over the optimal commute time. And again, it turns out in the network with the teleporter, you cannot do better than that 50-50 split. Okay, that turns out to be optimal. So that, I think, hopefully jogs your memory of what we've already discussed back in lecture 1. There's actually an even simpler so-called selfish routing network, which shows you that the price of anarchy can be 4/3. So that was from 1968. Let's go back even further to 1920. Where in his book, The Economics of Welfare, A.C. Pigou discussed, at least qualitatively, the following example. So he said, what if there's just 2 parallel roads? Okay, so literally Highway 101 and Highway 280 connecting Stanford to San Francisco. So just to make the example kind of as stark as possible, let's use these same, totally flat and then identity function cost functions. Okay? So what do we expect to happen at the equilibrium here? Again, assume there's 1 unit of traffic overall. So what would you do as a driver? Take the top or take the bottom? Yeah, so here we again have a dominant strategy, it turns out, in this particular network. So it's always a good idea to take the top. The best case, the worst case scenario on the top is as good as the best case scenario on the bottom. So does it seem like, could you do better with respect to the average commute time if I could move some of the people around, if I was a dictator of this system? In fact, anything would be better, actually, than this equilibrium. Okay? So it turns out the optimal thing to do is a 50-50 split. It's a simple calculation. So what's the average commute time with a 50-50 split? So half the people take an hour, half take a half an hour, right? So it's on average, it's 45 minutes. So again, the price of anarchy is 1 divided by 3/4 or 4/3. We'll discuss to what extent this 4/3 is or is not a coincidence later in lecture. All right, but let me come clean. Turns out even in these simple routing networks, okay, so if the price of anarchy was always 4/3 no matter what, arguably we'd be pretty happy. Because remember, this is a system where we're exerting zero control at all. We're just letting people do whatever they want. And if they inadvertently wind up getting a pretty good approximation of this hypothetical optimal solution, we're going to define that as a well-functioning system. Okay? So we'd actually be happy if this was the worst we ever saw, 4/3. Turns out I don't have to tweak this example too much to show you that in these routing networks, the price of anarchy can unfortunately be much larger. So let's look at a nonlinear version of Pigou's example. So we keep everything the same, except instead of this function c of x equal x, I'm going to make it c of x equal d, x to the d. We should think of d as large. 10, 100, 1,000, some large number. Okay. So how does this affect what happens at equilibrium, changing d equal 1 to d equals some large number? No change. Okay? It's still a dominant strategy to take the top edge. When everybody does that, you still get a solution in which the average commute time, in fact, the common commute time is an hour. Okay? So selfish solution still costs 1. What about the optimal solution? So even if you just keep the 50-50 split, already the optimal solution is going to improve as d grows large, right? Because on the bottom, you'll still have these half of the people that have an hour travel time on the bottom, but that 50% on the top, their travel time is going to be x to the d, or 1/2 raised to the d, okay? So as d grows large, that's going to 0, okay? So those people on top are getting there instantaneously. So that will already give you a factor 2, okay? Because opt would drop to 0.5. But in fact, the situation is even more serious. The optimal flow can do even better, because why bother putting as many as 1/2 on the link of constant cost 1? Why not just sacrifice a very small number of martyrs to the link with constant cost 1? You're going to have a 1 minus epsilon fraction of the traffic on the bottom link. Their common cost will be 1 minus epsilon raised to the d. 1 minus epsilon is less than 1, so as you keep powering up, it's again just going to 0. Okay, so you can find an optimal solution where almost everybody gets to t almost instantaneously, and then there's a few unlucky people who are taking an hour, but they contribute very little to the average. So a little more formally. So the optimal average commute time is epsilon times 1. So what I'm doing here is I'm putting epsilon on bottom, 1 minus epsilon on top. So the epsilon on the bottom contribute epsilon times 1 to the average, and then the rest of the average is the 1 minus epsilon fraction of the people who have travel time 1 minus epsilon raised to the d. Okay? So for any given d, I could solve for the optimal epsilon, but what's going to be true is as I take d larger and larger, the optimal epsilon is going to be smaller and smaller. And in the limit, as d goes to infinity and epsilon goes to 0, this optimal cost is actually going to 0. And therefore the ratio between the equilibrium commute time, which is 1 for every d, and the optimal commute time, which is going to 0 with d, this is blowing up to infinity. Okay? So in conclusion, price of anarchy goes to infinity as d goes to infinity and epsilon goes to 0. Okay? So we're seeing already in these very simple traffic networks, even in just 2 node 2-link examples, sometimes for whatever reason the price of anarchy is good, i.e. it's close to 1, sometimes it's not. Okay? So the best we can do as analysts is understand as thoroughly as possible, when are these networks, when do they function well and when do they not. Okay? So that's the question that we want to answer as thoroughly as possible in this lecture. When, that is, under what conditions is the price of anarchy of selfish routing small? Where small means as close to 1 as possible. Okay? So what might be hoped for? Well, for example, I've shown you 3 different networks. Okay, I've shown you one Brace's paradox where the price of anarchy is 4/3, not too bad. I've shown you another one, Pigu's example, where the price of anarchy is 4/3, not too bad. But then I showed you the nonlinear variant where it is bad. Okay? And if you're feeling kind of very cavalier, maybe you'd look at these 3 examples and say, what's the coolest fact I could imagine possibly proving, given what I know is true? And you say, okay, well, obviously an obstruction to having a price of anarchy close to 1 is having highly nonlinear cost functions. If you have these, x to the d's for super big D, you can't prove anything, right? The nonlinear Pigu's example shows that. So if you're feeling very optimistic, you might conjecture that's the only obstruction. Okay? So as long as you didn't have very nonlinear cost functions, you're going to be fine. For example, maybe at least if you knew that the cost functions were linear or affine, so of the form ax plus b, like in Brace's paradox and Pigu's example, maybe as long as the cost functions are affine, the price of anarchy is not too bad. Okay? That's kind of the strongest statement that might be true given what I've shown you so far. Turns out it is true. I'll show you proof in this lecture. Let me pin down the model a little bit more before I explain the statement we're going to prove today. So in general, we have a directed graph, okay, with an origin S and a destination T. This is given, and you're also told how much traffic there is. So our units of flow or of traffic are to go from S to T in a directed graph G with edge set E, vertex set V. Okay. I'm assuming one origin, one destination. Everything I proved to you about these selfish routing networks remains true even if there are multiple origins and multiple destinations. And I'll ask you to do that extension on exercise set number 6. It's really exactly the same proofs, just a little extra notation. So to keep the notation down in lecture, I'm going to assume one origin and one destination. And then the only other ingredient in the model, so you have the network, and then you have the edge cost functions. So I'm going to use C sub E. That's a C sub E to denote the cost function of an edge. I want to emphasize this is the cost of the travel time per unit. Okay? So for example, if it's 30 minutes, all traffic on that edge takes 30 minutes. Okay? So it's per unit of traffic. And we'll add some extra assumptions as we need to derive good bounds. But the baseline assumptions are very minimal. No time machines. Travel times are non-negative. Traffic's only bad. So cost functions are non-decreasing. They can be constant, that's fine. But they can't go down. And I'm going to want them to be continuous. Okay? So those are the baseline assumptions, but in your mind as you go through this lecture today, go ahead and, if you want, think about just the affine cost function case. I'm fine with you just keeping that as a concrete running example in your mind. So what are we going to prove? Let me explain the result a little bit informally. Then I'll develop the definitions that let me state it precisely. But let me just tell you conceptually what we're going to establish today. This is an old result of mine. So the main result is going to say that always, worst case examples are extremely simple, just like that Pigou's example that you already saw. That's the high level message. So among all networks with cost functions in the set C. So to state this, I'm going to parameterize by a set script C. These are the permitted cost functions. So for example, the set C might be the set of affine functions, all functions of the form AX plus B. Okay? Or maybe it's going to be a bigger set. Okay? And of course, the bigger the set, the more networks I'm trying to prove a statement about. So the worst case price of anarchy is only going to be going up as I permit more and more cost functions in this set. But for now, go ahead and think of this set C as just the affine functions AX plus B. Okay? It turns out the proof is sort of easiest to state at a higher level of abstraction, and that's why I'm doing it. Okay? So search the world, all networks in the world. The one restriction is that you can only annotate your edges with cost functions in C. You have to obey that rule. And I claim that when you come back from your search of all networks in the world, hunting for the largest price of anarchy ever, you're going to come back and you're going to show me a dirt simple network. You're going to show me a network that looks like the Pigou network. 2 nodes and 2 links. Okay? You will have looked at all of the more complicated networks. You won't have found a larger price of anarchy. Okay? It's not going to happen. So obviously the next order of business is going to be making this more precise. What's a Pigou-like network? What do I really mean? Okay, but I wanted to start with kind of conceptually what the mathematical statement is going to mean. So let me also just sort of say why you might care about this formulation of it. So as a special case, just looking ahead a little bit, this theorem will imply as a corollary, as a special case, I lost it, that among all networks, no matter how complicated, that have affine cost functions, the worst one is just that 1 in X Pigou's example. Okay? For networks with affine cost functions, nothing is worse than the 1 in X. Okay? So worst case examples are simple. And as a consequence, if you want to know what the worst case price of anarchy is, this theorem reduces that question to a dirt simple computation. Okay? This theorem is basically going to hand you a network with 2 nodes and 2 links, and it's going to say whatever the worst case price of anarchy is, it's whatever it is in this network. So now you just do a back of the envelope calculation on this network, and it gives you the magic number. So for affine cost functions, it hands you the 1 in X example. We already did the computation that the price of anarchy is 4/3 in Pigou's example. So as a consequence, the worst case price of anarchy in any network with affine cost functions is 4/3. The benefit of phrasing it this way is that it's not just about affine cost functions. This is a generic statement, whatever the set of cost functions. The magic number will be different, but this characterization of worst case examples remains the same. So by virtue of worst case examples being guaranteed to be simple, it is straightforward to compute the worst case price of anarchy for any class of cost functions you might care about. So again, let me just again help you interpret this. So, as special cases of this general theorem, as I just said, you get that the worst price of anarchy is 4/3 if we take the permitted cost functions to be affine cost functions, that is degree 1 polynomials with non-negative coefficients. If you, for example, allow the degree to go up to 2, what this theorem will tell you is that the worst example is just the Pigou's example except with the x replaced by x squared. There's just 1 and x squared. Now you just compute the price of anarchy in that network, and this theorem tells you that's the worst in any network. So that turns out to be roughly 1.6 for the d equals 2 case. Squiggle 1.6. Again, d equals 3. The worst case example is 1 and x cubed. So that's going to be like 1.9. D equals 4 is an interesting case because at least at one point in time in transportation, some people were advocating using quartic functions to model travel time of real traffic, okay, of actual transportation traffic. So the worst case example for quartic functions, of course, is just 1 and x to the 4th. That turns out to be 2.1. So in transportation models that were considered appropriate by some researchers, you got a price of anarchy reasonably close to 1, just 2.1 in the worst case. Okay? And in general, this is growing sublinear in the degree bound D. Okay? This is, of course, going off to infinity. We already knew that. We already knew without a degree bound, there was no bound possible in the price of anarchy. So what we're doing in this lecture through this result is we're giving a precise answer to this question. I gave you 3 examples. In 2 cases, the price of anarchy was small. In 1 case, it wasn't. We wanted to understand when is it small and when is it not. So highly nonlinear cost functions are an obstruction. They can cause large price of anarchy. And this theorem is a converse. It says if your network, no matter how complicated it is, has cost functions that are well modeled by low degree polynomials, then under no other assumptions the price of anarchy is close to 1. Okay? So when is it small? It's small, in the worst case even, when cost functions are not too nonlinear. That's the answer. Okay? So that's how that theorem answers this question. All right, so let me tell you about the plan for the rest of the lecture. So the first thing I want to do is I want to give a formal definition of Pigou-like networks, tell you what I mean in this theorem statement. Step 2 is we're going to define, using these Pigou-like networks, a lower bound on the price of anarchy. So this is analogous to our 4/3 lower bound for the affine case provided by Pigou's example. So we'll have a generic version of that 4/3 lower bound. And then the final part of the lecture will prove a matching upper bound for any network, not just these trivial Pigou-like networks. Okay, so that's the plan. Any questions before we do those 3 steps? Okay. All right, so again, define Pigou-like networks, use them to derive a lower bound, and prove a matching upper bound in any network. That's what we got to do. So, definition. So what's a Pigou-like network? Well, it has only 2 nodes, namely S and T, the source and the destination, and only 2 parallel links. Okay, so every Pigou-like network, by definition, looks like this. Okay? But that's not all. I will give you 2 free parameters. Okay, so the first free parameter is the amount of traffic, which I'll call a traffic rate. You can pick that to be any positive number, real number that you want. Okay? It doesn't have to be 1. It could be anything. I also, as a second free parameter, allow you to pick the cost function of one of the links. So you can assign the top link any cost function you want. Okay, so if we have in the background a set of permitted cost functions like affine cost functions, then this is any function you want from that permitted set. Okay? So one link has a cost function, C, but those are the only two parameters that you get, free parameters. So given the choice of the traffic rate R, given the choice of the top link's cost function, I insist that the other link has a constant cost. Okay, like in Pigu's example, we had a 1. It's going to be a constant cost, and I even insist on the constant. The constant is the cost function of the top link C, evaluated at the full traffic rate R. Okay. So this is a function, like x, depends on how much traffic. This is just a constant, a number, okay, like 1. Okay. So that's a Pigu-like network. Two free parameters, the traffic rates, and the cost function of the top edge. Don't want to do that. Questions thus far? So that was step 1. Step 1 was just to formally define what do I mean by Pigu-like networks. Now, remember, for a given set of cost functions, like for example the affine cost functions, our goal is to determine the worst, i.e. the largest, price of anarchy we're ever going to see in any network whose cost functions lie in that set of permitted functions. So for example, any network with affine cost functions. Now, to lower bound this quantity is a worst case over all networks in the world. So to lower bound the quantity, all I have to do is exhibit a single example. So like Pigu's example already gives us a lower bound of 4/3. Okay? So lower bounds on the price of anarchy are easy. We just exhibit examples. So step 2 is just to formalize this. Say, well, one place we can look for bad examples is these Pigu-like networks. Yeah, there's a lot of other things we could try, okay? But let's just start simple. Let's just say how big a lower bound, how strong a lower bound can we get just by confining our attention to these Pigu-like examples and nothing else. Okay? So that's what we're going to do now, formalize that idea. All right. So definition. Oops. Sorry. So the reason I defined Pigu-like examples the way that I did, okay, is that they're really easy to reason about. Okay? It's really easy to figure out what the equilibrium flow is in a Pigu-like network, and therefore it's really easy to understand what the price of anarchy is, the ratio between how well an equilibrium is and how good an optimal solution is. Okay? So let's just go through that.
Can you say again why finding a specific example gives you a lower bound?
So the price of anarchy for a set of games is defined as, so far I've defined the price of anarchy in a single game. Okay, in a single game, you look at the equilibrium, you put that on top. You look at the optimal solution, you put that on bottom. So that assigns a number to every single game. I'm defining the price of anarchy of a set of games, like for example, all networks with affine cost functions. So that's an infinite set of games. So I'm defining the set's price of anarchy as the largest, i.e. worst, price of anarchy of any game in the set. So to lower bound that, I just need to show you one. Okay, upper bounding it is the non-trivial part. Yeah. So we're doing worst case analysis of the price of anarchy. That's sort of the point. Okay, notes. So I claim Pigu-like networks are easy to reason about. Okay? So what is the equilibrium of a Pigu-like network? What do the selfish drivers do, selfish traffic do? So I take the top path. Basically what I did is I said, look, I give you two parameters, tell me what they are. Tell me your R, tell me your cost function C. And now I'm going to set the constant on the lower link just high enough that even when the top link is fully congested, no one's tempted to use it. Okay? So if everyone's on the top link, they all incur cost C of R, and I make the cost on the bottom exactly C of R. Okay? So the upshot, it's a dominant strategy again for people to take the top link, so everyone on top gives us an equilibrium. Yeah?
And the cost functions are non-decreasing?
That's right. That's one of the baseline assumptions. Non-negative, continuous, non-decreasing. Yeah. You're right. I mean, otherwise, what I just said would not be true. Yeah. But non-decreasing, so no one's tempted to go to the bottom. All right, so note, in a Pigou-like network, the equilibrium flow has all traffic on top. And as a result, we can just write down what the cost of the equilibrium flow is. So it's the travel time per unit of flow, okay, and that's C of R, because the top link is fully congested. All R units are there. That's the per unit cost times the amount of traffic. So R times C of R. Okay, amount of traffic, cost per unit of traffic. Okay, so in Pigou's example, this was just 1 times 1 for 1. Okay, now the optimal solution we're not going to try to characterize. Okay, so the optimal solution just somehow takes this R units of traffic, it puts some amount X, don't know what, but it puts some amount X on the top link, and it has to put the residual flow R minus X on the bottom link. And it does whatever it does. It picks the optimal X. Okay, that's all we're going to say about the optimal. So the point being is that the POA in an arbitrary Pigou-like network, well, it's just the ratio of the equilibrium cost, and we just said that was R times C of R. Now, if a flow, the optimal flow, if it puts X units on the top link, it's going to incur the per unit cost when there's X units of traffic times the amount of traffic on the top link, X. Again, this is conditioned on a choice of routing X on top. Everything else goes on the bottom. Everything else is R minus X. The bottom, remember, is this constant, always equal to C of R. Okay? So this is for a given choice of X. The optimal flow, by definition, chooses X to make the denominator as small as possible, or equivalently to make this ratio as large as possible. Okay? So we're going to do soup of all the legitimate choices of X. You can replace the soup by a max if you prefer, by compactness and continuity. Okay? So this is the equilibrium flow. The inf for the denominator is the optimal flow, so by definition this ratio is exactly the price of anarchy in a particular Pigou-like network. Okay? All right. So here's a quick technical point. No real conceptual content, just convenient for later. I claim that actually, if I erase this upper bound on the choice of X, then the number doesn't change. Okay? And again, that's just useful later. Why is that true? Well, think about when X is equal to R. Okay, first of all. I just claim that if I set X equal to R and then I make it even bigger, then the denominator gets even bigger. So this ratio gets only worse. Okay, so it's not an optimal solution. It doesn't attain the soup. So if I set X to be R and then I start increasing it, this is decreasing at a rate C of R, and this is increasing it at a rate at least C of R. Okay? So if you wanted to do this soup, there's no point in using a value bigger than R. So that's why I can get away with dropping the upper bound on R, on X, excuse me. So note, again, using that C is non-decreasing, I can drop the at most R without loss. Okay? Good. So now we're ready to formally say what do we mean by the strongest lower bound provided by Pigou-like examples. So what we've said so far, this expression for a given choice of R and a given choice of the cost function C, so for instantiations of the two free parameters, this is exactly the price of anarchy of the corresponding Pigou-like network. So if we want to do our worst, if we want to exhibit the largest, strongest lower bound, we should just optimize over our two free parameters. Okay, so we just want a worst case choice of the traffic rate R and a worst case choice of the cost function C, worst case meaning to make this quantity as big as possible. Okay, so that's the next definition. So let's C be a set of cost functions the Pigou bound which I'm going to note by alpha of C is defined as the worst POA in a Pigou-like network with cost functions in C, which we just argued is you take a worst case choice of the first free parameter, which cost function you put on the top link. You take a worst case choice of the second parameter, meaning the choice of the traffic rate R, and then you just write down the same thing we had before, okay? So what I'm writing here is exactly what we had before. Okay? Say it again? Speak up.
Don't you want one of those to be C of R?
Yes. Thank you. Thank you. Okay. So I know it's a lot of symbols, but just remember we arrived at these symbols as just the natural outgrowth of something, conceptually straightforward. We have this collection of examples that we understand, Pigou-like networks. Any given Pigou-like network gives us a lower bound. And we just said, well, what kind of lower bound can we get just using these? Okay? And this is just the symbolic representation of that idea. There's three supremums. Two of them are just because there are two free parameters in a Pigou-like network, the cost function, the traffic rate. The third supremum is just because I'm being lazy about figuring out what the optimal is. It's just the best case choice of X. All right? So it's a lot of symbols, but to express something really very simple. Okay. So I'll ask you to understand this quantity a little bit better, this Pigou bound a little bit better on the current problem set. So for example, if C is the affine functions, okay, so AX plus B, AB non-negative, or even in fact all concave functions that are non-negative, then the Pigou bound is exactly 4/3. I've already told you it's at least 4/3 because I showed you a Pigou-like network with affine cost functions that got 4/3. So all this is saying is, if you try replacing the 1 and the x with some other constant, some other affine cost function, it doesn't help. Okay, you can't do 4/3 by twiddling around with the coefficients in Pigou's example. That's all it's saying. And in fact, you can even the problems that will ask you to go through other things like for bounded degree polynomials. Okay, and you get this d over log d dependence. In particular, for low degree polynomials, alpha of C is reasonably close to 1. Okay? So what that computation tells us is that, okay, if our very modest ambition is just to understand how bad Pigou-like examples can be, Pigou-like examples aren't that bad. Okay? That's all we've done thus far. Okay? It says amongst examples with 2 nodes, 2 links, and a constant cost function, this alpha of C, if you do this computation on problem set number 3, the price of anarchy is pretty close to 1 for low degree polynomials. What's interesting is to ask about, well, what about there's a whole world out there beyond these trivial Pigou-like examples. Okay, how do we know that the price of anarchy doesn't grow with the network size? I have not yet shown you a network with more than 4 nodes. Okay, so that you should have no reason to believe that the price of anarchy stays constant as I scale up these networks to arbitrarily large size. Okay, and that's the main part of the theorem, the main part of this lecture. Give me any network with these cost functions, the price of anarchy doesn't go up, doesn't matter. Okay, all right. So by construction, really by the definition of the Pigou bound, for a set of cost functions C, alpha of C, the Pigou bound is a lower bound on the price of anarchy. Okay, each of these is a legitimate network that we could exhibit. We take the worst of those lower bounds, and that's still a legitimate lower bound. And now the formal version of the main result is as follows. For any set of cost functions, as always, the cost functions are non-negative, non-decreasing, and continuous. But other than that, it can be any set of functions you want. And now the main point is for all networks, no matter how big, with cost functions in C, the price of anarchy in such a network is upper bounded by the Pigou bound. Okay? So again, we know this is a lower bound. This is a lower bound achieved already in trivial networks. This is an upper bound for any network. So that's why we conclude, as a consequence, that worst case networks are always simple, okay? No matter what the cost functions are. Okay? And again, computing alpha of C is not such a big deal. So knowing that alpha of C achieves the worst case price of anarchy reduces computing the worst case to just on these simple networks, okay, which I'm asking you to do on the homework. All right? Okay. So the original formulation and proof of this is an old result of mine. The proof I'm going to show you today benefits from simplifications by a few different people. So Amir Ronen, and also by a subsequent paper by Correa, Schulz, and Steer and Moses. So any questions before we start talking about the proof of this theorem? I glossed over that. It's an excellent comment. So that's for the lower bound. It's not for the upper bound. So the question was pointing out that I'm actually cheating in a small way. Okay? So if you look at the definition of a Pigou-like network, okay, I use one cost function, C of something, and then I use a constant cost function. So to really claim that this Pigou-like network is a legitimate lower bound for a set of cost functions C better include the constant functions, because I'm using that on one of the links in my example. So yes. So for the lower bound only, you want to assume that. There are various weaker assumptions that are also sufficient, but that's the simplest version. For the upper bound, which is what I'm going to prove, you don't need any such assumption. Yeah, good comment. Other questions? All right, so I need to do some preliminaries before we prove this. And the preliminaries will be very familiar to anyone who's, say, taken CS 261 or worked with flows. The reason I have to do these is because so far we've only talked about equilibria in very simple networks where it's kind of obvious what they are. So we just really, to be rigorous, we should pin down what are flows, what are equilibria, and what are the costs of flows in a general network. So let's do that real quick. So consider a graph with source and destination. Okay, so ST network with R units of traffic. And all the points that I'm going to try to make in the next few minutes are already illustrated by the Brace's paradox graph. So everything I'm about to say, I would just try to interpret on the Brace's paradox graph with the teleporter involved. Okay? So what do we really mean by a flow? Well, a flow just explains how the R units of traffic are split over the paths of the graph. Okay? So formally, it's a non-negative vector. Sorry. On the ST paths, script P of G. And of course, it should be the case that the total amount of flow sums to the total amount of traffic. Okay? So with sum over the flows over the paths equal to R. So for example, in the Brace's paradox network, if we say there's one unit of traffic, a legitimate flow would be to route 50% on the zigzag and 25% on the two-hop paths. Okay? So there's 3 ST paths in this graph. I show you a way of splitting one unit of traffic over the 3. Okay? So that'd be a flow. Now sometimes, in fact often, we're going to want to zoom in and understand what's going on a single edge of the network. The reason Pigou-like networks are so simple is because edges and paths are the same thing. Not so in a network like the Brace paradox network. A particular edge in this network participates in more than one path. Okay? So we will write for a given edge, we zoom in, and by f sub e, I just mean the total amount of flow that at some point crosses this edge in its path. Okay? So I just sum over the paths that contain the edge, and I look at how much flow it puts on that edge. So for example, how about this edge right here? So consider this flow, the 25, 25, 50 flow. Upper left edge. What's f sub e for the upper left edge? .75, right? There's a contribution of 0.5 from the zigzag and 0.25 from the upper two-hop path. So that's going to be 0.75 on that edge, symmetrically 0.75 on that edge. How about this one? 0.25, same thing here. How about the 0 for the teleporter? 0.5, only the zigzag uses that. Okay? So given flows on paths, we can zoom in on an edge and ask how much total flow crosses this path. Okay? So when is a flow in equilibrium? Well, the intuition, I hope, is clear. Okay? The intuition is just if you look at any path that some traffic actually uses, that better get to the destination as quickly as possible. Better be the shortest path. Okay? So all flow should be on shortest paths. Now, it's sort of more subtle than that, right? Because which paths are the shortest also depends on what people are doing, right? So like in the Brace paradox network, or before we added the teleporter, if everybody's on the top path, then the bottom path is the shorter one. If everyone's on the bottom path, then the top path is the shorter one. So when we say everybody's using a shortest path, it has to be with respect to the current traffic pattern, with respect to the congestion on all of the edges. Okay? So here's the definition in general of an equilibrium flow. It should be the case. So a flow is at equilibrium if and only if it meets the following condition. So an equilibrium flow F. It should be the case that whenever a flow from S to T is actually in use, it has to be the case that this is the shortest path. Okay. And again, what does shortest path mean? We say, well, let's look at how much traffic is on each of the edges in the path and add them up. Okay, so I write FE here. That's the traffic under this traffic pattern on the edge E. What's the travel time along the path? Well, it just adds over the edges in the path. Okay. And as a shorthand, I will abbreviate this notation as the cost of a path P with respect to a traffic pattern F. Okay? So if you, a traffic pattern or a flow. I'm going to use flow and traffic pattern interchangeably. Okay? So for example, suppose I add cost functions now to this network. Suppose I add the canonical cost functions, x0, x1, 1. Is this flow in equilibrium in this network? Why not? What's the violation of that condition? So the first question is, there's 3 paths in this graph. Okay, I've fixed the flow. So let's just ask how short are the 3 paths, okay, given this flow? Well, how about the top path? So with respect to this orange flow, what's the travel time along the top? 1.75, exactly. 0.75 here, because there's 0.75 traffic on it, plus 1. Okay, by symmetry, same thing on the bottom, 1.75. So those are paths that are being used, but they're not shortest paths. Okay, the zigzag path is 0.75 plus 0.75, 1.5, less. Okay? So the violation of the equilibrium condition in this flow is that some path in use, in fact 2 of them, are not minimizers, are not shortest paths. Okay? And so I hope it's intuitively clear that any such violation we shouldn't call an equilibrium. Okay, if some path is in use and longer than all the rest, there's an incentive for people on that path to switch to load balance, to switch to one that's shorter. Okay? So this is the definition. This is what it means to be at equilibrium. There's 2 facts about equilibrium flows that for today I want you to take on faith. We will understand why they are true next week. Okay? So the first fact is that an equilibrium flow exists. So when we prove theorems about equilibrium flows, they're not vacuous. Okay? We actually are talking about something. Again, we'll see why this is true later on. And then, as I've stated, the price of anarchy, hold on. All right, so last ingredient of the preliminaries, the objective function. Okay, so remember the price of anarchy is the ratio of these, travel times. So how do you express the travel time for a flow in a general network? There's actually 2 ways to do it, and it's important you're familiar with both of the ways to do it. You can either count up travel time over paths, or it's exactly the same to count it up edge by edge. Okay? So let me write down the formulas and then we can go back to the Bayes paradox graph and interpret it. So our objective function, the quantity we'd love to minimize given the option. So first I'll just write it down in terms of the paths. So we just want to accumulate all the travel time that anyone experiences. And so just like in figure-like networks, we looked at an edge and we said, what's the travel time, how many people experience it? Here we're going to look at a path. Okay, so for a given path P, we just say, what's the per unit travel time on a path? Remember, C sub P of F is just the sum of the travel times of the constituent edges. So that's just how long it takes you overall to get from S to T. So that's the travel time, like 1.75 from S to T. F sub P, that's how much traffic incurs that travel time. And we better make sure we account for everybody. So we just sum over all the paths in the network. Okay? So that's the way you count up travel time path by path. The other way you can do it, which is exactly the same thing, but I'll leave it to you to verify, is you can go edge by edge. Okay? So in other words, you say, let's zoom in on an edge. What is the travel time that people experience just on this one road? Let's look at how much of the traffic at some point experiences that travel time. And again, let's make sure we account for everything by summing over all of the edges. Okay? The equivalence of these 2 things is literally just a reversal of sums. Okay? I'll leave it to you if you're unsure about that. So all this would say is that if we wanted to compute the total travel time of this orange flow, we could do it in 2 ways. We could either say, okay, 0.5 of the traffic has travel time 1.5, and then this other 0.5 has travel time 1.75. That would be the path-based way of counting. Or we could just say, look, 0.75 experiences 0.75 here, same deal here, 0.25 experiences 1 here, same thing here, and that's a 0. That would be the edge-by-edge way of counting up the same thing. Okay? But it turns out in the two parts of the proof of the theorem, the first part is going to be useful to think about paths, and the second part is going to be useful to think about edges. So I really do need them both. Okay? All right. And then the one other fact, I told you I wanted you to take one fact on faith. Equilibrium flows exist. The other fact I want you to take on faith is that they're essentially unique. And by essentially unique, I mean that while there can be multiple equilibria, they all have exactly the same cost. So there's no reason to care about which equilibria we're at. Okay, they're all basically the same. So fact. And again, we'll see why this is true next week. And I mentioned this because I'm stating all these theorems about the price of anarchy. What is it exactly? Well, it's the cost or the travel time. Okay. Yes, let me have some notation for this. So I'm going to abbreviate this by capital C of F. And the price of anarchy, by definition, is then just the cost of an equilibrium flow over the cost of the optimal flow. Okay? And by the two facts I told you, this is well defined. Okay? So the numerator is talking about a non-empty set. There's an equilibrium flow, and all of them evaluate to exactly the same cost. Okay, so I don't have to worry about which one I stick in top. Okay? All right, so we're done with the preliminaries. You should now feel comfortable talking about flows in general networks, when they're at equilibrium, when they're not, and how we measure how good they are using this total travel time. Okay, so given all that, we can now get to the interesting part and prove this. Any questions? Okay. Yeah.
So we know the worst case travel time is going to be achieved at an equilibrium flow?
Good question. So you mean like worst case over the paths?
Over all flows. Yeah, over all flows. I mean, should the cost of anarchy is the cost of the worst flow, right? Over cost of optimum.
So I guess what I'm saying is here I don't even need to define that. Right? So if there were multiple equilibria that were fundamentally different, I would actually have a non-trivial modeling decision to make, which is do I measure, so suppose I have a system with multiple equilibria, and I want to say some statement about equilibria. Now I have to figure out which one do I say something about. Okay, so Wednesday we'll have to deal with that issue. This model is really nice because all equilibria are the same. So there's no need to even make a decision. Okay?
Because we know that when anarchy reigns, we're going to achieve an equilibrium.
We'll talk about that also. So another excellent question is, it's all fine and good to prove these bounds about the equilibrium of your system, but how do you know you're at an equilibrium? So we'll discuss that at some length, actually. So that's the more kind of, second generation results on price of anarchy. Okay, but we're going to start by assuming, in effect, by celebrating a bound about equilibria, we're implicitly kind of assuming that it's meaningful. We're assuming the system is at an equilibrium. So that'll be our assumptions for this week. We'll relax those in lectures to come. Other questions?
Flows is that referring to the whole graph, like the allocation of what's going where?
Yes, so a flow by definition is a vector on the ST paths. Okay, so like in the network I just hid, there were these 3 ST paths. And so that's what we're talking about. So that was somehow the flow is being split amongst the ST paths.
So is one flow that the allocation over the entire graph, or would you say like there's a flow here and a flow here and a flow?
Flow is usually the entire vector, entire set of vectors.
Okay.
Yeah. Okay. So the main thing we're going to need from the preliminaries in the proof of this theorem, in addition to just this definition, is we're going to need to remember what the objective function is. Okay, these 2 ways of writing about the cost of the flow. Okay, so that's the one thing I'm going to really use. Okay, so proof of main result. So now we have to think about any network at all. Okay, and again, for the lecture, I'm assuming there's a single source and a single destination. In fact, the theorem even extends to multiple sources and multiple destinations. But so fix G. The only assumption is that the cost functions lie in some set C. And again, think of C as affine if you like. Okay. So fundamentally, I need to compare these two numbers. Okay, how well an equilibrium flow does and how well the optimal flow does. So F will be an equilibrium flow. F star is an optimal flow. Okay? So stars will always be optimal. No star will always be equilibrium. 2 parts. Neither one is that long. And in fact, conceptually, part 1 is very straightforward. Okay? The culmination of part 1 will just make precise the following statement. So if you have an equilibrium flow, and then I freeze the cost of every edge at that amount. Okay? So remember, every edge has its cost function. There's a lot of traffic, it's expensive, it takes a long time. If there's not much traffic, it doesn't take that long. But suppose we put the equilibrium flow in the network, and I just freeze all the costs, and they all become constants. This is a thought experiment. So the claim will be, if I do that, okay, if the costs are frozen, then nothing is better than the equilibrium flow with respect to these frozen costs. And the reason is just, by definition, equilibria route flow on shortest paths. Like, what else could you do that would be better? Okay? So that's going to be part 1, just making that precise. Okay. So since F is an equilibrium flow, whenever there's positive flow on a path, positive traffic on a path, we know the cost of that path with respect to the traffic pattern F, with respect to the equilibrium traffic pattern, is as good as that of any other path. Okay? So in particular, suppose I just look at 2 different paths, both of which are used by the equilibria. What can you say about the travel times along 2 paths, both in use in equilibrium? Yeah, they're the same. Right? So I just instantiate this twice, once with each path. All right? So at an equilibrium, all paths in use have a common travel time. And that travel time is no larger than that along any other path. Okay? So I'm going to use the notation capital L for the common length of all of these paths that are in use by the equilibrium. Okay? So let L be the common length of all equilibrium flow paths. Okay, so now again, what we're shooting for is we're just saying if we freeze the costs in this state, this equilibrium is as good as anything else. Nothing else is better. Okay, so formally, let's look at the cost of the equilibrium. Okay, so remember, for this first part, I'm going to be using the path-based way of counting up cost, counting up travel time. So we sum over the paths. We look at how many are on the path. We look at the cost of that path. So this is the equilibrium. So for every term here, one of two things is true. Okay? Either FP is 0, the flow isn't, this path isn't even being used, and we don't care. Or if it's in use, we know that the length of the path is exactly capital L. Okay? So this sum becomes very simple to evaluate for the equilibrium flow. This is just equal to L whenever we have a positive coefficient. And this thing just sums to R. Okay? This is the flow. So it's actually very easy to understand the cost of the total travel time in the equilibrium flow. It's just the per unit cost that everybody incurs times the amount of flow that's incurring it. Okay? And let's keep these frozen and look at F star. Okay? So I guess one thing to remember is, so F star is this optimal flow. Okay? It's beating the equilibrium flow. It's better than it. Okay? But remember, one of the reasons it's going to be better than it is because it's going to have different costs, right? It might have less congestion on some edge. Remember, think about Pigu's example, right? So the equilibrium puts a full unit of flow on the X, making it cost 1. The optimal uses it in moderation, puts only a half there, has cost only a half. Okay? So they have different cost functions. We're doing this weird thought experiment where we penalize the optimal flow by freezing them at the equilibrium level. Okay? So I'm going to write down a quantity which doesn't make a lot of sense, but it's useful for the proof, which is I look at the optimal flow. Okay, so F star is how it spreads its traffic, but for whatever reason, I evaluate path lengths as if the equilibrium flow is in the network. Okay, that's what I'm doing. And again, this is extremely easy, maybe not to evaluate, but at least to lower bound. And again, the intuition is just the equilibrium is on shortest paths. How can you do better than that? Okay? So precisely, this is at least capital L, right? And again, this evaluates to R. So that's what we mean by freezing the edge cost at the equilibrium levels. No other flow can be better. Let me just rewrite this so that it exports better to part 2. Okay? So this was easiest to see using the path way of accounting for travel time, but I want to have it in the edge form. So this is at least this. Equivalently, if I sum over edges, sorry, that's at most that. So if I sum over edges instead, this is an equivalent statement. Okay, again, I take the optimal flow amounts, but I use the equilibrium costs to evaluate it. That's the same statement. And then again, exactly the same statement, and the form I'm going to use it in part 2. Let me just subtract that from that side. Okay? So this is what I'm going to need from part 1 in part 2. Okay? Again, the intuition remains the same. If you freeze the costs at the equilibrium levels, you can't do better than routing entirely on shortest paths. Okay. So part 2. So very roughly, this is a little inaccurate, but sort of what we're going to do in part 2. Notice we haven't used we haven't used anything yet. Part 1 is really just about equilibrium flows. I haven't referenced what the cost functions are. I haven't referenced the Pigou bound, nothing like that. Okay? So sort of morally, what we're doing in part 2 is we're going to say, well, let's zoom in on a given edge and argue that on each edge separately, it looks enough like a Pigou-like network that we're not going to be doing worse than the Pigou bound alpha of C when we compare how the equilibrium does and how the optimum does on a given edge E. So the dream would be we zoom in on an edge and we say the equilibrium cost is no more than alpha times the optimal cost, and then we sum that inequality over all of the edges and we'd be done. That'd be the dream, this edge by edge example. That's not quite going to work. There's going to be edges where there's more equilibrium flow. There's going to be edges where there's more optimal flow. It's kind of hard to say it's really like a Pigou-like network. But we'll say, it's like a Pigou-like network on each edge up to some error term. And it turns out the collection of error terms we'll be able to control using this conclusion of part 1. Okay? So roughly, we're going to treat each edge like its own Pigou-like network, roughly. Okay? All right, so here's where we use the definition of the Pigou bound. Okay, so let me remind you what that is. We're working with this set C of cost functions. The Pigou bound just says it's the largest price of anarchy you ever see in a Pigou-like network. So you take a worst case choice of the top link's cost function. You take a worst case choice of the traffic rate. That's the equilibrium cost in the Pigou-like network. This is the optimal cost for the best case choice of X, and the ratio is the price of anarchy. Okay? So we know that is what it is. Because this is a worst case choice, if we instantiate C and R and X, if we take particular values of those 3 parameters, that right-hand side will only be less, will only be upper bounded by alpha of C, because alpha is the worst case, the largest choice. Okay? So any instantiation of these gives us a number that's upper bounded by the Pigou bound. So how do we instantiate We do it separately for each edge of the network. So again, we're zooming in on an edge, okay? So there's only, there's one cost function on the edge, there's one cost function in this expression. So of course we instantiate that outer supremum to be this cost function. We think of the equilibrium flow. So again, keep in mind, we were given this graph G. There's some equilibrium flow, there's some optimal flow. What we're doing is on an arbitrary edge, we're sort of zooming in, okay? It has some cost function. There's some amount of equilibrium flow here. We'll interpret that as a traffic rate in the Pigou bound. There's some amount of optimal flow on this edge E. We interpret that as the choice of the splitting x. Okay? So this is a particular way to instantiate these three things. So this quantity with those instantiations is at most alpha of c. Okay, so I'm just plugging these three things into that formula. Okay. Believe it or not, we're almost there. Okay. All we have to do is rearrange and sum and then interpret, and we'll be done. So let's swap denominators. So let's remember what I'm trying to do is I'm trying to say the equilibrium is near optimal. It's not much more than the optimal flow f star, or equivalently, I'm trying to lower bound f star, saying it's at least a large fraction, less than 1, but a large fraction of the equilibrium cost. So let's just rearrange this to isolate the cost incurred by the optimal flow f star on this edge E that we've zoomed in on. And we get something actually kind of suggestive. Okay, so again, once we divide through, we get a 1 over alpha times that equilibrium cost on this edge. So this inequality here is what I said was the dream, where you just zoom in on an edge and you say the equilibrium is not doing much worse on the optimum on this edge, and then you just sum over the edges. That's what that would be if that were true. Okay? So again, alpha is something like 4/3. So this would say that on this edge, f stars get it incurring at least 3/4 of the equilibrium. Okay? But the dream's kind of not, quite fulfilled. We have this error term. So plus f star e minus fe times ce of fe. Okay, that's the residual after rearranging. Let's sum over all the edges. So what do we get if we sum this over all the edges? This is just the cost of f star. Remember, one way to count up the cost of a flow is you do it edge by edge. Look at the cost of the edge with respect to the traffic pattern. Look at how much traffic incurs it. That's exactly what this is. So if we sum on the left-hand side, we get exactly what we want to lower bound, the optimal flow. By exactly the same reasoning, right? This is just some constant, right? This is just like 3/4 or something. By the exact same reason, if we sum, this term summed over all the edges, this is just the total travel time in the equilibrium flow, f. Then we have the sum of the error terms. I've tried to let things unfurl on the board so that it's rather clear how we control some of the error terms. What do we know about it? The whole point of part 1 was to show that that was non-negative. Okay? That's in the box. Okay? So what's in the box says this is non-negative. Again, it just says, look, this is basically saying the edge costs are frozen at the equilibrium amounts. And we're just looking at we're comparing opt to the equilibrium. And the equilibrium is as good as it gets if you freeze the edge costs at the equilibrium amounts. So this is non-negative. Therefore, if we drop it, we still have a legitimate lower bound. Okay? So by part 1, meaning this thing, we get exactly what we wanted. That the optimal flow is at least a 1 over alpha fraction of the equilibrium flow, or if you prefer, that the equilibrium costs no more than alpha, the Pigou bound, times the cost of the optimal. Apologies for going over. I'll see you on Wednesday.